Yeah, let's make a start. Hello, everyone. Thanks for watching this video. So in this video, I'm going to show how to use FlowPy to construct a simulation case for ModelFlow 6. ModelFlow 6 is a widely used software package to simulate groundwater flow and has many useful packages such as recharge, lakes, streams, and everything. So it can basically cover almost all the aspects involved in groundwater flow and also the surface water and groundwater interactions. And FlowPy is a very useful package. It's Python-based script language to construct the input for model flow. And later on, you can use FlowPy to extract data from the simulation result and do the post-day analysis. It's very powerful. So I've been using two different types of inputs and software. So one of the way is that you have the graphic input, where you can drag and click to construct your input and then do the analysis for the output in the same way. But for this type of thing, the issue is that, first of all, the software package will update. So you will feel that the work that you've been done a couple of years ago is not compatible to the newer version. And turns out you have to construct from scratch. This is one. Whereas using FlowPy, it's Python-based. Usually, a model could be reconstructed even a couple of years later. So referring previous project would be very handy if we use FlowPy. The second thing is that once the script is being written, it's very straightforward to adjust and also conduct the sensitivity analysis, just changing the numbers. So it's much handy as compared to the graphic user interface based constructor. That being said, I'm not playing down the importance of using graphic user interface because in some cases it's very useful, but for this instance, I'm going to use FlowPy. So for this particular case, we have connected field data. So some of the field data, such as surface water depth, will be used as input. So there is an issue here, say, when we got the data from the field, it's probably being recorded once per hour, whereas my time step is completely in different time intervals. So in that case, we need to use spline interpolation to basically interpolate the field data to the point where the time step is. And that requires a bit interpolation, which I'll explain. And also, once we constructed the model, there will be verifications against the field data. So we got to the groundwater head from a few boreholes. So the simulated groundwater head over time will be verified against that from the field, which is a verification. We will also give you my way of doing sensitivity analysis. It's very handy, so you can see that how using a script based model constructor, how can we do a quick sensitivity analysis. And finally, I just need to mention so far the boundary packages we will be using is recharge package, constant head package for the boundaries. First, I need to say that maybe for advanced FlowPy user, they probably will use different packages to solve the same problem. But this is basically, first of all, a preliminary outcome from the work that we've done so far. And later on, we can use advanced package. Second is that the purpose of this video is mostly for educational purposes. So we start from simplest and then step into complex boundary conditions. Before we move into the model construction, I would like to share how the field condition look like. So this is the slide. So what happens to this field site is that there is a pond formed by pumping. the pond has a more or less a diameter of 200 meters. It's not ideally spherical, but it looks quite like a jelly bean. So within the pond, we have several boreholes, which is about 8 meters down to the sandy aquifer. So this is SA2, more or less at the center of the pond. And there is another monitoring bore, which is at the boundary of the basin, which is also down to 8 meters below. There are also 2 other monitoring bores outside of the pond, which has never been inundated. So if we artificially form this pond, what will happen is that the water will infiltrate to the aquifer underneath, and the water table will be bulged, will be increased. And such increase of water table will be dissipated to all the directions, so that SA1 and SA4, the 2 bores, will also sense a little bit rise of the dissipation. And then it dissipates indefinitely until it becomes almost the normal water table. And other than infiltration, there are also evapotranspiration from the pond, which takes the water out. And eventually the pond will be disappear as the water depleted by both recharge and evapotranspiration. So there is a simple mass balance here. So pond storage plus unsaturated zone storage is equal to pumping flow plus rainfall minus ET minus recharge. But for this case, we only look at the water table induced by recharge, and recharge is being treated as a source term to the aquifer. So another simple sketch to look at the process is that we got water, I have a better version to explain what we did here, so I just need to open up this file. It's just being stored in a different, okay, so this would be better. So once the pond is formed, you see the pond base is not uniform. So every different locations has different depths. So even we measure a height of 1 meter, it doesn't necessarily mean that everywhere is 1 meter, because some of the area is higher. So that means the water depth is not only time dependent, but also space dependent, right? The depth of the unsaturated zone is quite deep. It's about 6 meters. And the rise of the water table is very small. It's about only up to 2 meters. Only at the tip, at the middle, the rest of the places are very small. So we basically assume that the depth of the unsaturated zone does not change with the rise of the water table. So strictly speaking, the depth is here. But let's just, as a beginning, let's assume that the depth of the unsaturated zone is basically a constant of L. And we have a hydraulic conductivity of K, which is also constant. So if we have this type of very simple model, we could assume that recharge rate is equal to, this is pretty much like a Darcy flow. First is the hydraulic gradient. It's the depth of the water table, water level, plus the distance, the depth of the unsaturated zone over the whole unsaturated zone times a hydraulic conductivity. So basically, this is the gradient. This is the head differences. This is the traveling distance, and the whole thing is the gradient times a hydraulic conductivity is equal to recharge. And in that case, at every location, the recharge rate will be different because the depth is different. At different times, the surface water depth is also different. And in that case, the bathymetry of the pond needs to be considered. The change in water depth in time and space needs to be used as input of the model, right? So that's basically how the recharge will be considered in our model. And I said there are some fancy packages like Lake package that can solve the problem better, but we just try to make it simple as a recharge package. It's more straightforward, and later on we can move to some fancy packages. So I copied this slide to the other PowerPoint and delete this one. Okay, so have a quick look at how the field condition looks like. So if we look at the water depth change measured at this location, you will see that it's rising up to 0.8 meters and dropping down due to rain, due to evapotranspiration and recharge and infiltration, more strictly speaking. And then the water level rises due to a second pump, and then it's falling down, becoming zero as the surface completely depleted. And then we pump the water in to a height of 0.8, and it started to decrease. So as a response to the groundwater table, so SA2 is right in the middle. And then you can see that the rise of the water table is, well, from this one is about almost 2 meters. The reason that they start from 14 is because once we deploy the sensor, we basically put it to a certain depth. So it's not only about at a certain depth, so they have an initial hydraulic static pressure, but it increases. The actual rise is about 1 meter. And the reason that it has a significant rise is because before the water comes in, we basically pump the water out from the bowl. So it started recovering. So the recovering is affected by groundwater moving from ambient conditions to the middle rather than recharge. So the rise has been justified as 1 meter. So SA3 also has a certain rise as well. It also was pumped before the inundation. So the rise of the water table is about 2 meters. And there are the other two balls outside of the basin. So each of them has roughly 200 mils rise of water table. And then once it's increased to the top, and then it decreases. And that really means that the water table is start of going down because the recharge is reduced. And the reason the recharge is reduced is because the surface water depth is decreasing. So the gradient decreases. The other reason, which we've been investigating, is that the clay tends to swell as it wets. So the permeability could somehow be reduced as well. But this is not an issue that we are going to investigate. And then we pump the water again, increases to this level, and you can see that the groundwater head has a tiny responses. And then as the surface water becomes depleted, you can see that the water table almost reduced to the original condition. So this is also a reference point that where is actually a static water table. And then we pump the water again, you see the rise, but this rise is very different from the original one. So originally rise up to that high, but the second time the rise is only half of what's being achieved from the first time, which is a clear indication that the saturated clay has relatively less permeability due to the swelling. And the swelling is affected by the bentonite and smectite, which tends to swell as it wets. But the change in hydraulic conductivity is not something we're going to discuss today. There are something that we need to pinpoint here is that you see some of the drop and rise. And this drop of rise was because we went on site to do the borehole water sampling. So we basically empty the borehole, and that obviously will draw down the water table and bring it back. But this type of tiny events is not going to be simulated by the model. So once we compare the result, we're not going to compare with we are not going to include this type of events. So this data needs to filter out this type of events, which I'll explain how we're going to do it. So this overall gives you a situation about what happens to the field and what the model looks like. So I would like to show you how the setup is looking like. It looks like. So I'll put this one in here. So here is the aerial view, so like a bird view of the domain. The domain is about 300 meters in X direction and then 300 meters in Y direction. And the pond is assumed to be spherical and a circular, let's say. And so the surface elevation, it's not strictly flat. Instead, it has a depth distribution. So I'll show you, this is the depth. So you can see that in the middle of the pond, the elevation is about -2.5. And outside of the pond, it's equal to 0. So in that case, you can see that when the water depth is, let's say, 0.15, the recharge is only taking place right in the middle, and the rest of the cells are considered to be dry. So only a tiny little recharge. So the recharge cells changes as the surface water depth change. So this is something we need to consider. So that explains what the black region is. So that's where the recharge zone is located. And again, it doesn't mean each cell will be subjected to recharge. It's only when the cell is being inundated. 3 monitoring points. So blue points corresponds to SA2. Red points corresponds to SA3. The blue line corresponds to either SA1 or SA4, which is outside of the pond. We're going to use observation package to extract data from these 3 points and then compare against the groundwater head measure at these 3 points. The other thing that we implemented for this model is that all the cells hatched in blue are considered as a constant head. So this is being identified when we deploy the balls where the groundwater depth among all the balls are literally flat. So within this whole floodplain, there is no gradient of groundwater as it approaches to the river, given that the floodplain is relatively large. In general, groundwater head tends to be following the surface topography. And given that the floodplain is relatively flat, so we didn't really see a significant head and fall as it approached to the river. So as a simplicity, we basically put into a constant head. So what the result probably will look like, so I'll probably show the result first. That gives some kind of indication. So these are the sensitivity analysis, but you can see that the water level, so this is the head. This is the head at one transect right in the middle. So the top level, the middle of the pond has the highest water level, and then it dissipates laterally. And at the boundary condition, it becomes the constant head boundaries. And we also compare the groundwater head with the monitor data. So the dots are the field data, and then the lines are the simulated data. So there are 3 locations. The water depths are considered as input. And the recharge rate at different locations are also being plotted. So remember, SA3 is outside of the pond. So once the water, it is at the boundary of the pond. So imagine if the water recedes, let's say 80% of the full, SA3 is exposed to the air. So the recharge stopped. And later on, if we look at the SA2, which is right in the middle at the lowest point, that stop of recharge takes place much later as compared to the SA3, which indicates that we properly considered the process that when surface water depth draw down, the recharge region is decreasing. Yeah, so that's what the result will be look like. So we basically show the result, and then we discuss that how it's being implemented. The script is being uploaded to a GitHub site, which is given here. I'll give that to the YouTube link so that you can download. So within that upload, I got two types of files. So one is IPYNB, the other one is Python file. So Python file is easily being used in, let's say, Spider. So within Spider, you could open up the file and then run it, and then you basically run through the whole thing, and all the output is shown here. So let's say I can close the whole kernel and then start again. And usually for me, that I tended to choose, let's say, a run in console's namespace rather than an empty one, so that all the variables inside the simulation will be reassessed. So if you don't click this, after you run the program, all the variables disappear, so you can't do any debug. So to me, I prefer to keep all the variables so that later on you can just try to type some simple equations to implement more functionality. So this is one of the things that I would recommend everyone to use. The second thing is that when you start running the program, let's say, you know, we find out the file. Let's say model flow Jupyter.py. So that's the file. I tended to right click and then I set console's working directory. So you need to ensure that the working directory is just at the location where the file is located. And then you can run by just click run file. You see that things are popping out and it's running the whole procedure. So it takes a bit of time, but not too long. And so you can see something popping out. The other thing that I usually do, that I'm basically just give all the tricks that I use for do this modeling. So as you can see, if we run here, all the plots popped out in here. But it doesn't give you any kind of interactive way to, you know, maneuver in the graph or even zoom in and zoom out, which is not quite handy. What you could do to allow the graph pop out is that you get this, you run this line, say get Python, run line magic, auto. So if I copy and paste in here, now let's say I wanted to run this graph. Well, I have a title here. So I can Control F, say 3D view. Okay, so this code section is to create this graph. But instead of putting it here as a static image, I want them to pop it out so that I can Control Enter. So I just press the Control and Enter. It only runs that specific cell. So the cell is being separated by this symbol here. And it only runs this tiny one. So then you can see it ends up with an interactive interface here where I can move around. So that basically shows the surface topography of the pond. So the lowest point is about negative 0.25. The top is about 0. So it gives you a bit flexibility. The other thing that I would like to show, this is something I usually, you know, step into it and then examine it. So this is the 3D view. The second thing is during the interpolation. So I have this graph here. So that's called interpolate surface water depth. Okay, so this one, so yeah, that's set title. So I can run this whole thing. Again, I'm using Control plus Enter. So that one pops out. And then, well, in this graph, what happens is that the red line is the measured data. The crosses are the interpreted result based on the time steps. Because let's say my time step is 5 seconds, whereas the field monitoring is once per hour. Then I need to fill in all the gaps, and then the gap is being filled by interpolation. So if I zoom in here, you can see that it has sort of daily fluctuations due to the fluctuation of the atmospheric pressure. But nevertheless, I only need data at the specific point for comparison. So, so I can use zoom in function, which is just the drag, and then to see whether the zoom in is okay. So I can go back. So this one does require a specific interface to zoom in and zoom out. One of the other things that I also would like to show is that for this x-axis, it only show the years and months, but it doesn't show date and hours. If you see my top right of the picture, just about my head, there's X and Y, and again, it's only year and month. So if you want to get hours, you can zoom in. So first zoom in to a tiny little area. Now you can see the dates already appears about my head. And if you further zoom in, you probably are able to get minutes. So this one tells you month, day, and hours. So basically that helps you to say, oh, which is the important time that I need to do some processes. Then you can do that. So that's also the interface that I tended to use in the Spider interface. Well, one of the things, I need to say is that in Python interface, you need to install a few packages. Let's say it's been given here. So you need to install, CSAPS. You also need to install Mat, Plotlib, and also FlowPy, those packages. So how are you going to install these? So it's going to use Anaconda. So it's called Anaconda prompt. So you click this, and then you will be able to install pip install, let's say NumPy. Yeah, so let's just assume that you're gonna install the package, because you need to have these packages to be able to run your to construct your model. So it's already said that NumPy is being installed. So that's for this one. The other thing that I also identified is that we tended to use the newest version of FlowPy. So currently the newest version of the FlowPy, let me have a look, and is it doesn't say here, so let's run this, is actually 3.3.5 at the moment. So if you git pull, you probably find out the FlowPy version. If you use pip install FlowPy, you probably have a version that is less than this. So to be able to get the newest FlowPy, what you could do is that you first git clone. So the way of doing it is that you first search FlowPy and then get these. You get the FlowPy address copy, right? So that's where FlowPy is. And then you get a command interface that has git there. So I have git in my Linux in Windows. So I have Git here. So you just use Git clone, and then this whole thing. So that's the key command here. So it takes a while for Git FlowPy to come to your computer. And you can cd into it and then install it. So let's say currently I did that command. I get FlowPy here, right? I get my FlowPy. So that's where the cloned FlowPy is. And I need to install that into my Spyder. So the way how you do it, you go back to the other command line, which is these, right? So I go to D and then cd project. Well, that space, that separator is backslash FlowPy, right? And then you can do Python setup.py install. So that's basically the command that you install FlowPy from the instance rather than pip. So that could guarantee you to have the up-to-date FlowPy, particularly some of the packages may require the newest version. So in that case, you can get that. Now, this is all about using Spyder. How about if I use IPYND notebook? So we could run notebook. So I have one notebook running. So I basically can cancel it right now. And then I rerun it. So the command is given as, it has to be in the Anaconda prompt. So the command is set as Jupyter. Well, I tended to use lab rather than notebook because lab becomes very up to date. I really like some of the function, which I will show you. And the notebook directory is D because my C drive is for Windows rather than Linux, rather than storage files. So I tended to start with D. So I can press that. And then you'll be able to get a Jupyter interface very, very soon. So as you can see now, it started off running and then something popped out. And then you are able to get a Jupyter Lab interface. Yeah. So again, this location is localhost, which means that you can only run that from your local computer. I have another separate video posted a few days ago that show you how you can access this remotely. But this is not going to be repeated here. So if we're going to use Firefox instead, so I can copy the whole thing and paste it here. And then you will see they open it up. And then we can do all the analysis here. So I need to go to projects. That's where my Git package are. And then we probably need to model flow. And then I need to open it up. That's just too much. Okay, so that's where the file is located, right? And once we find this, we can basically put this one out. And then we probably will need 2 instances rather than 1. So in that case, I can file, open new views for notebook. So see now I've got 2 views. And so it's very handy for me to basically editing somewhere at the very bottom and then try to search from the top panels. And it's easy to reference. So that's a very important functionality. The third thing that I usually use for Jupyter Lab is that you could do new consoles for notebook. So the console is here. So if you want to have some interactive commands, let's say, you know, let's make a simple example. So let's run my my cell here. So cell 2 and cell 3. Yeah. So my cell 3 is completed. Oh, it hasn't finished yet. Really? Okay. It started connecting. So it hasn't been connected to the system yet. Why it's still connecting? Okay, let's select that. Okay, so it's, can we run it? A is equal to 5. I'm basically just trying to check whether that works. So shift enter, A is equal to 5, but it's not being executed. So what we can do is to restart the kernel and see whether that will solve the problem. No kernel. Interesting. Does this one works? So probably I can cancel this and start restarting. It hasn't started yet. How about this one? Does this one work? Well, we literally just need to find out whatever that works. Okay, have a look at whether it seems to be frozen. Because I didn't see any feedback from this. So what I'll do, okay, so now I basically stopped the server. So you see that it's stopped so that I can leave page. Oopsie. I think I need to share my screen again, the whole screen. Yeah, share. Okay. And then we need to basically run the same command again and see whether we are able to get JupyterLab. Because I want to show the whole program through JupyterLab. That's why I intended to make the JupyterLab working for everyone. So it's all up to you what type of user interface are you going to do for run the program. It's all up to you. So I'm basically trying to move this again, stay on page, leave page. And see whether that works again. So now I open it up. I'll do these. So you see that once I use Control and Enter, you will see that's been changed to 1, which means that the script is executed. To check it, you can do is that File, New Console for Notebook, and then I can put it into npmm. And then I use my Shift Enter. You will see that it ends up with the number that is here, which indicates that this program is running, is executed. Now, we got that working. So let's just move over to here. So I basically minimize this, and then I can further zoom in. Now, what we can do before we start, have an overview so that we then go to the nitty-gritties. So I restart the kernel, rerun the whole thing. You will see it has start. Start means that this cell has yet executed. It's waiting for execution. So 5 means it's being finished. So 10, 11, 12. So we move all the way down. And see this line has yet completed. We just need to wait a bit longer time until it's being executed. It might finish just very quickly. Or is that being stuck? No. So you see the program is running 7, 18, 19, 40. And then the final big one. Okay, so we got the results. So that's basically the IPYNB file. Now I need to move one line by one line to explain how I managed to get that results. using FlowPy. The first cell is a just an explanation. So it's all being hatched, commented. You're probably already aware that instead of doing code, you can make it as a markdown. The reason I didn't use markdown is because I sometimes change the code back and forth using Python and IPYNB. Storing file in IPYNB in GitHub is useful given that the output is also here. So if I push this to GitHub, you will see the final result. And then 5 years later, when you refer to that code, you can see what the result probably looks like. It gives more detail about the code rather than just it's just the input Python file. You don't know what you produce. So the preview to me becomes very important. The other thing I also would like to share for you is that once you've been using Modelflow, you probably will use it for a while for a few projects and then busy on something else, and then you come back to Modelflow. And then you would have your previous cases there as a reference. So your previous cases has several boundary conditions implemented. So you can always copy and paste codes from there. As the time goes, you probably have 10, 20 examples there ready for you. And next time, if you need to work for another groundwater project, it would be very quickly for you to prototype and set up the domain because you have already gone through many cases. So it's always important to create your own repository so that you can always come back and see how those boundary conditions was being configured. And that will be easily copy and paste to your new project. So that's what I've been doing. The second cell is about importing all the things. So it's OS, SYS, NumPy, Matplotlib for plotting. Pandas is very important. It's panel data, which I'll show you how that works. Also, we need to import FlowPy. So it has two ways of importing. So one is to assume that FlowPy is in your system The second one is that it's installed locally. So you're basically running an example of the FlowPy instances downloaded from GitHub. Either way, as long as it's been imported, they will pass these lines. Now, we've got print. So we print SYS version, we print NumPy, we print Matplotlib, Pandas, and FlowPy. These are very important, actually. So you see that after the cell, the output is displayed here. The reason I say that's important is because in some cases, I realized that some of the code only works at the specific version. So if we basically push the IPYNB file, those things are stored in the IPYNB file. And 5 years later, I'm pretty sure all those versions are already being updated. And it's possible that the new version of those packages are not able to reproduce the old result. So one of the things you probably can do is to roll back to the previous versions and then rerun the code. That gives you a better likelihood of getting exactly what you got a few years back. So that's why IPYNB is very important. So I would recommend every time you construct a project, try to copy and paste this piece of code as a benchmarking. And a few years later, you know exactly what type of package you use to construct this model. Then we have some initial parameters for plotting. So you can probably just copy and paste. It gives sizes of the fonts and also the figure size. So it's kind of default values. And the model working directory is called current dot point and data. So it means that when in your working directory, which is here, so that's, sorry, it's here. So you would have a file of directory called data. And here you've got your field data. So we got pond depths at SA2, water tables at 4 locations. So that's where you get all the the data. So I said pond depth will be input, water tables at 4 locations will be for verifications. And I also show that where is the working space. So working space, I said, is model flow planar 2D here. So that's exactly where I am. Now, the third cell is about some unit conversion. So I sometimes use I want to convert millimeters per to meters. So how does this work? So I would like to explain this. So to be able to do it interchangeably, I will say there's a new console. Okay. Now let's say if I have length meter is equal to 5, so millimeters. So let's say this variable defines a length that is 5 millimeters, and then I use Shift and Enter to run it. And now I need to change this unit to meters. So I can say length meters is equal to length millimeter, Control C, Control V, times this. Okay, so if you look at this, this line, it actually self-explains. Why? Because we know that the length millimeter is 5 millimeters, so it has a unit of millimeters. Now, if you consider this P as a slash, so M is actually in the numerator and MM is at the denominator. So you know that these two will be canceled and it ends up with a unit of M, which is this. And then if we run this by Shift and Enter, we know that the length M is going to be 0.005, which is being converted. So the reason that I like to use this type of unit conversion is that it's self-explained and it's easy to convert among different units. And as a starting user, the majority of the problem is actually unit conversion. And I do not tend to use the numbers here, because let's say 5 years later, you look at your code, you look at this number, and you probably think, oh, this is gravity, but it probably has a density as well. You always need to think about how can you explain the 1000 there? And it's always good to, just do this type of variables. So this variable here is to convert meter per second to meter square. So meter per second is hydraulic conductivity, and meter square is permeability. So if you have, let's say conductivity is meter per second, meter per second, which is 1⁻⁴. So that's basically like a sand. And then you can convert that conductivity to meter square, which is about 1⁻⁻11 meter square. As for sand, you see that this is already being executed. It should be -11 though. I think it's anyway. So we will check that later on. It should be -11. So it should have these anyway. Okay, now. Same thing applies to below. So if you have a hydraulic conductivity of meter per day, you could convert that into meter square, which is that function here. Now, let's move on. Okay, so cell number 3. Is that right? Let me just try to double check whether that number is correct right now. So that 1⁻⁴. If I do this, and then I do this. Okay, let's leave that for now. Right, so for number 4 here, this is something very important for sensitivity analysis. So what I created is a dictionary. The dictionary has a few parameters. So case ID, which is our ID, I call AH. Then KH stand, meters per day, which is 2. And then number of layers is 1. Specific yield is 0.03. Starting head is -6. And the clay hydraulic conductivity is this number. And then the bottom elevation is -10. The reason that I put it in here is because this is the values that I do for the sensitivity analysis. So you see there are a history of variables that I put about, which are already being executed. And later on, it's so easy for me to change those variables. So let's keep there. And then later on, I'll explain how I put this to, how I use this to do the sensitivity analysis. Now it comes to the domain. So the Lx is 300, which corresponds to the Lx, which is 300. So the Ly is 300, so same. The top elevation is 0. And then the bottom elevation is obtained from the sensitivity analysis, which is -10, yeah? And the number of layers is only 1, so that's 1 layer. So we start from 1 layer. The number of rows, number of cells in the row is 20. And the rows is given by these. So 300 to 50, sorry, rows is here. Column is this way, okay? So row, actually, this is something very funny. So the first row is actually at x is equal to 300, rather than x is equal to 0. And the column, the number of columns, let's close these. The number of columns is 20, which corresponds to these columns. So 1, 2, 3, 4, and then 20 columns. And then once we got the length and we got number of rows and columns, we can calculate the delta row with a unit of meters, and delta columns, which is in meters as well. And we also have the delta vertical thickness of each layer, which is by z top minus z bottom over n lay, which is 1. So in this setup, we end up with something as we show in, I'll probably close this presentation 1. Let's save it. And then I can go back to the other one to show. So you can see this head cross section. It's only 1 layer, and the starting from 0 and then finish at -20. So that's only 1 layer. Okay, so then we need to show what is the vertices for the elevation layer. And this is in the layer. So this L here means it's in layer directions, and it's a list. So I basically create a line space. So to be able to check the result, you can do it interactively through this command and Shift Enter. So that's 0, -10. So basically, if you have a layer which is 10 meters, you got your top pan and the bottom pan, and the top 10 is 0 and the bottom pan is -10. We need to change the bottom pan so that it has a kind of surface topography considering the basin, but that will be done later. So that's some of the input that we have finished. Now, so this NPER is number of stress period. So first of all, I need to explain what is stress period in model flow. So stress period basically so for all the mathematical model that is transient, you have your time domain. So I have the x-axis here. So that's a very quick, simple stress period explanation. So that's time, right? Now, stress period 350 means that you basically cut your whole time into 350 points. But this is slightly different from DNT, number of time step, because stress period, the keyword is stress. So in every single stress period, you can apply to a certain stress. What could be the stress? Let's say recharge. So the first time there is no recharge. So stress period, the recharge for the first stress period is 0. The recharge for the second stress period is 2 meters, let's say. Let's assume that's 2 meters. So that's corresponded to how the groundwater is receiving a stress. But within each stress period, you could have multiple time steps. So how to explain that? Let's say if you got a rainfall, and then during the rainfall, that's a stress period. And then after rainfall, there is no recharge, and then it's a second stress period. And then you don't apply any recharge during that time. And within each stress period, you could have multiple time steps. So just give a quick example. So this is a typical model that only have time steps. So you probably have even time steps. So TS1, TS2, TS3, TS4, and TS5. Whereas if you have a stress period, you could have one stress period, and then each stress period have time step. So that's a stress period 1, time step 1, stress period 2, time step 2, stress period 1, time step 3. So during this stress period, maybe there is no recharge, which means that these 3 time steps doesn't have a recharge. And we could, likewise, if we apply recharge for the stress period 2, that means SP2 TS1, SP2 TS2, and SP2 TS3 doesn't have recharge. So it gives a kind of, it groups all the time steps and then apply to a specific boundary conditions. So that's an advantage of using stress period. So go back to the script. Go back to the script. Now we got 350 stress period, and we didn't really specify the time. So T multi-array, which is 1. So I'll show you what does this mean. So in each stress period, the T multi is always equal to 1. So what is T multi? So here, if the time step splits average the stress period, that means it's 1. Whereas if it's greater than 1, your stress period tends to look like, I'm basically trying to give you a kind of graphical way to show. So that looks like 2. So you can see that as the time step increases, the step size increases as well. So it's uneven. But from our case, we tended to use an average time step that cuts the stress period, which means that the T multi is 1, right? So that, and the reason we need to make MP1s here is that we need to specify a T multi for every single stress period, right? So that's this. Now, the next one is number of time step per stress period. And so for this one, for me, I only use 1. So in that case, each stress period for me is 1 time step, right? And if we look at this graph here, this actually means that in each stress period, there are 3 time steps. So that one needs to be changed to 3. But for now, we just use 1 instead. So T multi again, so that's, I think this is redundant. We can cross it out. Now, that's the Boolean array to see whether each stress period will end up with a steady state condition. The answer is actually no, because that's why it's zeros. The reason is that the model is transient. None of the time step will reach to a steady state condition, right? The next one is that we basically create a stress period n time day array. Let's say this is CumSum, the T multi array day. So you will see that this basically shows you at the end of each stress period, what is the time? So if we go back to the graph we had here, so for my case here, at the end of the stress period, so this point is actually day 1, yeah, day 1. And here, the second would be day 2. And the next would be day 3. Day 3, yeah. So that gives that array for us to post the process, or array that is easy to it's easy to plot the results. So that's where we are here. The step interval for now, it's not being used. It's just to give you how often you need to extract the results. And kHsend is inherent from the kHsend meters per day, which is the parameters that we got from the large dictionary. So again, if you would like to show what is that value without moving up and down, what I can do is that I do a new view here. And then I can scroll it down to show, oh, okay, so kHsend is being well defined here as 2, right? So that's where it is. So that's very handy for us to cross-check. So I close it. And then I need to create the KH list. The list has 3 dimensions. The first is layers, row, and column. So I'll show you how does that work. So that's a big list, multiple dimensional list. And the reason I put the LRC is that if you want to get the first layer, the 4th row, and the 3rd column, that's what that value is. So the reason that I keep on using this is that we could create a lot of variables, but you sometimes could forget about what is the dimension. So if you put this one in your variables, it's easy to let you remember what is actually being stored in there and what is the dimensions. And in general, even the disadvantage is that the variable is too long. But once you look at your script 5 years later, you know exactly what that variable is, and I don't worry much about how long is the variable. It's easier for reference. And the VKA is basically the vertical hydraulic conductivity, which is a copy of these, which means that the aquifer is homogeneous. The specific yield is obtained from SY, which is 0.25. The specific storage here is 1⁻⁻⁴, which corresponds to how the aquifer could be compressed if it's a confined layer. So let me explain this, and then we will finish the tutorial today. So the graph, I have a graph here. So let's assume this is domain, groundwater domain, vertical 2D, and the line is water table. And actually, we've got 3 types of cells here. The first cell, which is very common, is that the water table is stay within this cell, right? So in that case, the hydraulic head of that cell is between 0 and -1. Well, one of the things I have to say is that model flow exports hydraulic head, not pressure head, which means it's elevation plus pressure. And if a specific yield for this layer is 0.25, that means when we have a recharge of 0.25, we can allow the head to increase by 1 meter. Yeah, so I'm explaining this again. If the SY is 0.25, that means once we recharge from the top to a thickness of 0.25 meter, the head is going to increase by 1 meter. And the reason is because the rest are all the solid particles. The rest of 0.75 is solid particles. Now, the second type of cells is the cells that is where the water table is above it. Let's say this one. So if you want to allow the water level to increase, you still need to somehow like inject water in this cell. But the injection is very, very small. That injection basically causes the aquifer domain to shrink. And how much does it take for this cell to rise ahead for about 1 meter? The answer is about 0.1 millimeter as specified by the storage storativity, which is here. So let's imagine if the head is here. Now we want water table to rise up to here. And the hydraulic head, the specific yield for this cell is 0.25, yeah? And the specific storage here is 1 power negative 4. The specific storage for this cell is 1 power negative 4. So literally, to allow water table to rise from this point to this point would be, for this, it would be 0.25 meters of recharge. For this one is 1 power negative 4. For this one is 1 power negative 4. So the number would be 0.2502. So you need to have a recharge of this much to be able to allow the water level rise from this point to the point. So in general, what does this mean is that once once the cell is confined, it actually will be squeezed due to the high pressure, which is specified by the specific storativity. And once it's a unconfined aquifer where the water table is within the cell, the specific yield is the key parameter to tell what is the pore space. Specific yield is more or less equal to effective porosity. So that's basically for the combined cell. So that's the second type. Now there are the third type, which is this cell. So you can see that this cell, water table is actually below it. In model flow, this cell is considered as inactive. So you will give a value of 1 power negative 30 to indicate that this cell is inactive. Once the water table rises to this cell, the inactive cell will change back to an active cell. But this is going to be discussed for our later discussions. So I hope that explained well about the specific yield and specific storage for you. I'll stop from here and then talk in our next videos about all the rest of the script. We've already run for nearly an hour. Yeah, thank you. Stop share and then finish the meeting.